Welcome dear learners. We are continuing transition and inner transition elements, a topic from inorganic chemistry. And in this module, we are discussing general characteristics of transition elements. We considered the transition elements properties in two parts. These are the transition elements. As we are aware, there are four different transition element series, namely the 3D series, 4D series, 5D series and 6D series. These 40 elements constitute the transition elements. We can enter into the details of the characteristic features of transition elements. The general characteristics of transition elements are entirely different from that of other blocks in the periodic table. That is, the transition elements exhibit some special features. These features can be related to their electronic arrangement. We can have a glimpse into the special characteristic features of the D block elements. The first and most important feature is their possibility to exhibit different oxidation state. That is, same element can exhibit multiple oxidation state. The picture represents different oxidation states of compounds of vanadium. Vanadium can exhibit 2+ state, 3+ state, 4+ and 5+ state. Similarly, manganese, which show wide variety of oxidation states. This is an important peculiarity of transition metals. The variable oxidation state shown by transition metal is attributed to the availability of electrons from n-1 shell and nth shell. That is, in the case of a D block element, it is possible to participate n-1 d electrons as well as ns electrons to chemical bonding. This leads to variable oxidation state. The energy difference between ultimate and penultimate shell is too small in this case, which made variable oxidation state possible. Variable oxidation state shown by 3D series of elements is shown in this chart. That is, 3D series of elements are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. For scandium, the most common oxidation state is +3 and for zinc it is +2. And the possibility of different oxidation state increases from left to the middle. At the same time, the possibility of showing higher oxidation state or different oxidation state also increases from right to middle. That is, the middle part element, that is chromium, manganese and iron, show maximum different oxidation states. The stabilities of different oxidation states are different. It is an important point. For example, iron exhibit oxidation state of Fe2+, that is ferrous ion, and Fe3+, that is ferric ion. Both will not have the same stability. Ferric is comparatively more stable than the ferrous arrangement. Okay. The oxidation state that we shown in the previous slide, that oxidation state increases towards the middle of the series from both sides. The D block elements can form ionic compound in their lower oxidation state. The ionic character decreases and covalent character increases with the increase in oxidation number, that is directly connected to the Fajan's rule. Now, coordination complexes. Coordination complexes, as you all aware, coordination complexes are formed by the coordinate bond between central transition metal and ions or ligands. That is, ligands are a species which is capable of donating at least a pair of electron. Even water can act as ligand, ammonia can act as ligand, Cn- can act as ligand. Several ligands are there, and coordination compounds and coordination chemistry is another important area belongs to inorganic chemistry. Then what is meant by coordination number of a coordination complex? The number of ligand atoms that are bonded directly to the central metal ion is termed as the coordination number. Then geometry. Number of ligands as well as coordination number controls the geometry of the molecule. The geometry or shape of a complex ion depends on two things. They are coordination number and nature of the central metal ion. The complex formation tendency is another characteristic feature of the d block element. We learned first property, chance for showing variable oxidation state, that is one important characteristic feature. This is another characteristic feature, that is nothing but the coordination complex formation tendency. The cations of d block elements are unique in their tendency to form coordination complexes with several ligands, several neutral ligands, charged ligands, etc. A ligand, as I already mentioned, is a species which can donate at least a pair of electron. Water can act as a neutral ligand. Cn minus can act as a negatively charged ligand. NO plus can act as a positively charged ligand. With the different type of ligands, coordination complexes can be formed by transition metal. That's another special feature. The complex forming tendency of these elements or d block elements is attributed to several factors. Let us analyze the factors which favor the coordination complex formation by a d block element. The favoring factors are small size and high positive charge density shown by the d block metal. Then the availability of vacant d orbital of right energy to accept the lone pair of electron. There is coordinate bond formation between ligand and the central metal. So, the central metal must accept a pair of electron given by the ligand. To accommodate that electron, there must be vacant orbital. In the case of the d block elements, there are vacant d orbital, and these vacant d orbital can easily accommodate the electrons donated by the ligand, which makes the complex formation more easier. Then exhibition of variable oxidation state. Variable oxidation state is also a factor that favor the formation of coordination complexes by the d block elements. Now, some typical coordination complexes are here with the different geometries and with the different coordination numbers. And for example, coordination number 2, that is 2 ligand around the central metal which exhibit a linear shape. These 2 ligands are separated by an angle of 180 degree. This is the linear shape, and this one represents the square planar shape. This is typical tetrahedral shape, just as in the case of our CH4 molecule methane. Okay, octahedral arrangement. These are various common geometries of the coordination complexes shown by the d block elements. Some typical examples are also there. For instance, CuCl2 minus, AgNH3 twice plus and AuCl2 minus are linear shaped molecule. NiCN 4 times 2 minus, its IUPAC name tetracyano nickel 2. Nickelate 2 is that coordination complex, exhibit square planar geometry. Then CdCl4 2 minus, MnCl4 2 minus, etc. with the same coordination number, exhibit the geometry tetrahedral. So, for coordination number 4, there are 2 common possible geometries, square planar and tetrahedral. We can consider all these things along with the coordination chemistry and coordination complexes and octahedral complexes. Typical examples are titanium hexa aqua TiH2 6 times 3 plus vanadium hexacyano complex, etc. So, there are several coordination complexes shown by the 3D series, 4D series, 5D series and even by the 6D series of transition metal. That is, the complex formation tendency is a special character of the transition metal. Now, regarding another feature, that is magnetic properties. Okay, we are familiar with the paramagnetism. Paramagnetic substances are weakly attracted by the magnetic field. At the same time, diamagnetic substances are repelled by the magnetic field. Some substances like iron oxide, etc., strongly attracted by the magnetic field. That is, they exhibit a strong degree of paramagnetism, simply termed as the ferromagnetism. So, several type of magnetic responses are familiar to you. And among the transition metal compounds, paramagnetism is more common. Paramagnetism is due to the presence of unpaired electrons. Yeah, okay. However, some metals in the elemental form and some of their compounds exhibit ferromagnetism also. Paramagnetism is feeble type of magnetism, whereas ferromagnetism is simply the strong degree of paramagnetism. Unpaired electrons are responsible for the magnetic response or magnetic behavior. If no such unpaired electrons are present, you can call such a species as diamagnetic, and such a species are repelled by the magnetic field. Now, the origin of magnetism in d block elements and their compounds. The electrons being charged particle, negatively charged particle, act as tiny bar magnet or tiny magnet as themselves. That is, each unpaired electron can be considered as a very small magnet. Unpaired electrons determine the magnetic properties in two different ways. That is, the electron, the unpaired electron, can execute two different type of motion. That is, the electron can spin about its own axis, as that is called the spin motion. The magnetic moment arises due to the spin motion of the electron is called the spin magnetic moment, and there is one more motion for the electron, just like Earth revolving around the sun, that is nothing but the planetary motion or simply the orbital motion. Electron can have orbital motion also, that is electron revolving around the nucleus through circular motion or orbital motion. That orbital motion of the unpaired electron also causes some magnetic moment, and that is termed as the orbital magnetic moment. So, an unpaired electron can provide two components to the magnetic moment, that is spin magnetic moment, which arises due to the spin motion, and orbital magnetic moment, which arises due to orbital motion. This picture represents the orbital motion as well as spin motion of the electron. Here this is the orbit. Electron is revolving around the nucleus through the orbit, that is termed as the orbital motion, and electron spins about its own axis also, that is termed as the spin motion. Thus, the origin of magnetism, that is the total magnetism, is due to two components. Spin motion leads it to spin magnetic moment, and orbital motion of the electron leads it to orbital magnetic moment. Then how we will get the total magnetic moment? The total magnetic moment is the sum of, simply the vector sum of spin magnetic moment as well as orbital magnetic moment. These two quantities added together to get atomic magnetic moment associated with the d block element or transition metal. The resultant of above two magnetism, spin magnetism as well as orbital contribution, leads it to total magnetic moment associated with the d block element. Now, magnetism is strictly connected to number of unpaired electrons. If there is no unpaired electron, you can say that there is no spin contribution as well as orbital contribution, such that the species termed as diamagnetic. And for the 3D series of metals, the electronic arrangement is shown here. In the case of scandium element itself, you can see the presence of one unpaired electron. And for titanium, the unpaired electron is 2. For vanadium, it is increased to 4. Then for chromium as well as manganese, for chromium due to exceptional configuration, it is D5, also one unpaired electron in S subshell. So for chromium, the total number of unpaired electron is 5 plus 1, that is the total number of unpaired electron is equal to 6. Okay, that is maximum number of unpaired electrons shown by any 3D series of metal is chromium. It is having highest number, 6 unpaired electrons during their electronic arrangement. And from this, except zinc, all have some unpaired electrons, and except zinc, all these elements of the 3D transition series can be considered as paramagnetic due to the presence of unpaired electrons in them. Then if we are taking some ionized cases, suppose our element iron will undergo ionization to produce some oxidation state like Fe2 plus or Fe3 plus. Okay, some unpaired electrons are removed from here and we will get arrangement. For example, if we are taking Fe2 plus, the electronic configuration will be D6, 3D6 will be the electronic arrangement. 3D6 can be simply represented by this 5d orbitals are this. Okay, the 6 electrons can be arranged like this, first one, second, third, 4, 5, this one is 6th. Okay, this electronic arrangement I shown here is purely based on Hund's rule of maximum multiplicity, and you can see 4 unpaired electron in Fe2 plus. In Fe3 plus, one more electron is removed, and that configuration is D5 configuration. D5 configuration is for Fe3 plus. So, Fe3 plus having 5 unpaired electrons. So, for transition metals as well as their unpaired electrons, the chance for the presence of unpaired electron is very high, and existence of magnetism is also high. Spin only magnetic moment. I simply mentioned the fact that the spin motion of the electron is responsible for spin only magnetic moment. The spin only magnetic moment is designated as mu s. In transition metal compounds, the spin component is dominating over orbital component. That means spin contribution is higher in magnitude compared to orbital component. Thus, in many cases, we are simply avoiding the orbital contribution for the sake of convenience to determine the total magnetic moment. And in many cases, we are avoiding the orbital contribution, and we calculate the spin only magnetic moment by using this equation mu spin only or mu s equal to under root n into n plus 2, where n represents number of unpaired electrons present in the system. From this it is clear that, from this equation it is clear that if the number of unpaired electron is high, the magnetic moment will also be high. The unit of the magnetic moment, it is simply Bm. We can call it as Bohr magneton, and one Bohr magneton is theoretically equal to Eh divided by 4 pi mc. E represents the charge, H represents Planck's constant. Yes, this formula mu s equal to under root n into n plus 2 Bohr magneton represents the spin only magnetic moment associated with the transition elements. The spin only magnetic moment can be computed based on the number of unpaired electrons and also based on the oxidation state. For scandium, we learned that the electronic configuration is 3d1 4s2. For scandium 3 plus, 4s2 electrons will vanish out, 1 d electron will also vanish out. So, the configuration is d0. That means there will be no unpaired electron at all, and hence scandium 3 plus is a diamagnetic species. That is mu observed is equal to 0 as well as mu spin only is equal to 0. Okay. For titanium 3 plus, 1 unpaired electron is there, and 1 unpaired electron means number of unpaired electron n is equal to 1. Therefore, the magnetic moment root of 1 into 1 plus 2, that is equal to root 3 Bohr magneton, that is equal to 1.73 Bohr magneton. For chromium 2 plus, the electronic arrangement is D4, that is 4 unpaired electrons are there, that is root of 4 into 6, that is root of 24. Okay. Root of 25 is equal to 5, root of 24 slightly less than 5, that is equal to 4.90. And for manganese 2 plus, the electronic arrangement is, for manganese, the electronic arrangement is 3d5 4s2. This is for manganese, elemental manganese. When you are removing 2 electrons from manganese, you will get Mn2 plus. For Mn2 plus, 4s will be 0 and the configuration will be 3d5. Okay. That is, in the case of manganese 2 plus, there are, you can see the presence of 5 unpaired electrons. That 5 unpaired electrons leads to a magnetism of root of 5 into 5 plus 2. That is root of 35. Root 36 is equal to 6. Root 35 is slightly less than 6, and its value is about 5.92 Bohr magneton. Okay. This chart represents the spin only magnetic moment of different transition metal cations, especially from the 3D transition series. And the spin only value calculated by this, we can also evaluate the magnetic moment of the transition metal systems based on some experimental methods like Gouis method, superconducting quantum interfering device, quid magnetometer, vibrating sample magnetometer. Several advanced technologies also there to measure the exact magnetic moment values of the transition metal ions. And these results shows the experimental or observed values. And the observed values are in very close agreement with the spin only value calculated. Some anomalies are there. That anomalies arise due to the orbital contribution. Total observed magnetic moment is a combination of spin component as well as orbital component. Here we calculated only the spin component. So, the spin component calculated may be slightly different from observed value, that is due to the involvement of the orbital contribution. Okay, that about the case. Now, this is another important peculiarity or special feature associated with transition metals, that is the formation of colored ions or colored compounds. This is a special feature. Several beautifully colored compounds are known and familiar to you. The majority of the compounds of D block elements, whether ionic or covalent, compound may be ionic or covalent, but they exhibit solution and they exhibit a color in solution. When the salt is dissolved in some solvent like water, we will get colored solutions. Okay, in solid state also they will exhibit some color. The color of D block metal ion is associated with incomplete d-subshell or incomplete d-subshell configuration of the central metal ion, as well as the nature of the surrounding groups or ligands or the surrounding media. These are the 3D series of elements. From the picture, the 3D series of elements, you can see most of them are colorless or dark. But whenever we enter into their compounds, we can see beautiful colors. This is scandium, titanium, vanadium, chromium, manganese. Copper is almost slightly red in color. Okay, but all other elements are having some dark color. This about the element. But whenever we are considering their compounds, we can see the beauty of different colors. These metals, the 3D transition series of metals, even though all have no color, they can form different colored solutions or different colored compounds. Now, let us analyze some compounds of 3D transition metal compounds for their color, and let us observe the color of some compounds. I will show you a demonstration, some common compounds for your consideration. First of all, potassium permanganate. The test tube contains a very dilute solution of potassium permanganate having a deep purple color or violet color, and the molecular formula of potassium permanganate is KMnO4, potassium permanganate. Here you can see that the central metal manganese is a transition metal, and this transition metal is present in +7 oxidation state. Manganese has no d electrons present in it, and the reason for this color, this intense color, is charge transfer transition. Charge transfer transition. Charge transfer transition, simply designated as CT, charge transfer transition. In a more clear way, we can say that the charge transfer transition occurring here in KMnO4 is ligand to metal charge transfer transition. That is, electrons are transferred from oxygen present in 2- state to manganese present in +7 state. This transition, this electronic transition, is responsible for this intense color of potassium permanganate. Now, we can consider another solution that is more common to you, that is copper sulfate solution. Here also some charge transfer transition as well as some DD transition occur there. The reason for color we can consider more detail in coming sessions. So, this pale blue color solution represents a dilute solution of copper sulfate. Now, we can consider another solution. This one is potassium chromate, that is K2CrO4, potassium chromate. This yellow colored solution is shown by potassium chromate. Here the central metal is chromium. Chromium is present in +6 oxidation state. Here there is also ligand to metal charge transfer transition, and I will show you on another compound of chromium, that is potassium dichromate. Potassium dichromate has the molecular formula K2Cr2O7. On analyzing the oxidation state of chromium, it is also +6. So, in potassium chromate as well as in potassium dichromate, the central metal chromium has oxidation state of +6. And you are familiar with this fact, chromium has an electronic configuration 3d5 4s1. So, for chromium +6, the electronic arrangement is 3d0 4s0. So, there are no d electrons. Then the color, the yellow color of K2CrO4 and this orange color of potassium dichromate is due to charge transfer transition. The most common reason for color is DD transition that we can consider soon. Okay. Now, I will show you one more intense color that is given by mercuric iodide. Mercuric iodide. This red color is due to the presence of mercuric iodide, HgI2. HgI2. Okay. So, there are several beautifully colored compounds are there, and the formation of colored compounds is a very special characteristic feature of our D block element or transition metals. Color of some aqueous solution is detailed in this chart. We saw some colors and more colors are shown in this picture. SC3 plus, it is colorless. Colorless is due to the presence of no unpaired electrons in the D subshell, that is of 3d0 configuration. That is here scandium 3 plus shows no color due to DD transition, due to the phenomenon of DD transition. Okay. Then titanium, vanadium, chromium etc. have some colors, purple color, green color etc. And these color shown here is not due to charge transfer. This color is based on DD transition. Okay. DD transition is an important phenomena where most of the coordination complexes and D block compounds show different colors. These are the three major reasons for color shown by D block elements or coordination complex or different compounds of D block elements. The first one is most popular DD transition. What do you mean by DD transition? We know that there are 5 d orbitals. The 5 d orbitals are dxy, dxz, dyz, d square y square and dz square. When an element converted to a compound, all these d orbitals will not have the same energy. That means these d orbitals splits in their energy and there is a chance for transfer of electron from low energy d orbital to high energy d orbital by absorbing some radiation, and as a result of such a transition, complementary color will be emitted. That is more common reason for the color of D block compound is DD transition. Second one is charge transfer transition, as I mentioned in the case of potassium permanganate, potassium dichromate, potassium chromate etc. Another one is polarization. That is a very rare reason for color in some silver halides. Silver chloride is a white precipitate. Silver bromide is a pale yellow substance. Silver iodide is a deep yellow solid. The reason for the color variation is due to different degree of polarization. So, polarization may also be a reason, in rare case, a reason for the color of coordination complex or simple ionic compounds or D block compounds. Now, another characteristic feature of D block metal is the metallic character. The D block elements are mainly preferably metals. They are good conductors of heat as well as electricity. They are malleable and ductile. Most of them or all of them except mercury are solids at room temperature. You know the fact that mercury is a metal which exists as a liquid at ordinary temperature or room temperature. Alloy formation tendency is another important characteristic feature of the D block element. The transition metal atoms have a similar atomic size. There is no much size difference between transition metal atoms, such that in the crystal lattice, one metal atom can be easily replaced by other metal giving solid solutions or alloys. The alloys are usually harder and have higher melting point than their parent or component metals. They are more resistant to corrosion than their constituent metals or constituent elements. Some very useful or important alloys. There are several enormous number of alloys are there, and some representative alloys are shown in this diagram. Brass, which is consisting of two metals, preferably copper and zinc, which is highly useful in making different type of utensils. Bronze, which comprised of copper and tin, used in the preparation of bells, coins and some utensils. German silver, see German silver contain no silver, but the composition comprised of copper, zinc and nickel, used for the preparation of several utensils. Rolled gold, that we use instead of gold in ornaments, comprised of copper and aluminum in making cheap ornaments compared to gold. So, in the present discussion, we considered several characteristic features such as variable oxidation state, magnetic properties, colored compound formation, alloy formation, etc. as the characteristic features of the transition metals. That's all about this presentation. Thank you all.